At 4 o'clock this afternoon is the undergraduate town hall meeting for CS and EECS and wannabe CS undergraduates to meet with faculty and administration of the department and discuss whatever concerns you have. It's at 4 o'clock. It's, I'm pretty sure, in the HP auditorium. I better know before the time comes because I'm going to be at it. So I'm one of the people you can ask questions of. And that means that my office hours, which usually run until 5, will end at 4 today. So sorry, but come to that instead. OK, so the big topic that's going to take up most of our time today is, where did they put my stool? No, that's not the big topic. Ah, there we go. That's a little topic. The big topic is how tables work. So what a table is an association between keys and values. And you've seen different kinds of tables by now. You've seen a two-dimensional table back when we did data-directed programming. And in the current programming project, you're seeing one-dimensional tables, but more than one of them. So you can create a table as needed. So we're going to talk about those different variants and all the different ways of doing things. The code on the screen here is for the simplest possible version where there's only one table and it's one-dimensional, because I like to start simple and work up. So the first thing is to talk about association lists, which are up on the top board there. An association list is a list whose elements are key value pairs. A key value pair is a pair whose car is a key and whose cdr is a value. So that's a pretty simple definition. It's a very useful idea to have in many, many situations. So much so that Scheme comes with procedures that know how to deal with association. Well, one procedure anyway that knows about association lists, and that's a sock key in association list, which returns a key value pair, or false. So if the thing you're looking for is in the association list, it doesn't return the value the way our table structure does. It returns a key value pair. And we'll see in just a moment that that's useful for allowing modifications to the table. It's also useful if you need to be able to distinguish a key that's associated with the value false from a key that isn't in the table at all. Because a sock, if it does find a match in the table, always returns a pair. So in one case, you get back a pair whose cdr is false. That's if the value in the table is false. Or you get just plain false, meaning that the key was not found in the association list. So let's go ahead and make an association list. Define a list to be the list, I don't know, John, rhythm, Paul, bass. Well, no, I should make it John dot rhythm, Paul dot bass, George dot lead, and Ringo dot drums. OK? So here's my association list. And now I can say a sock Paul, quote Paul, a list. And I get back not the word base, but the key value pair, whose car is the key I was looking for and whose cdr is anything. So if I say assoc Mick a list, I get back nothing because he's in the wrong group. Okay? Questions about association lists? Good. This association lists are a really, really, really ancient Lisp data structure. There have been A-lists since the very beginning in 1962 of Lisp. And they've survived, again, because they're really useful. Now, for making a table, the obvious thing to do is just use an association list as the table. That's not what we do. Instead, we have this yellow pair, which is a header. It sort of serves two purposes. You can view it as attaching a type tag. Right? So this is a thing of type table to the association list. But it's more important than that. It serves as what we call a sentinel, or sometimes dummy node. Those are names for this pair. Because the reason for sentinel is you put them at the front and maybe at the end of a list or an array. It's a very common technique, even in those other ways of doing things, to serve as endpoints, pseudo-elements of the structure. And this often saves you writing special case checks for running off the end. So sometimes, for example, you'll see algorithms for searching sorted elements in an array. And what they do is they put the value -infinity at the front, and they put the value infinity at the end. And so you're always guaranteed that anything you're looking for is within the limits of this array, even though those aren't really part of your data. And we're going to do sort of the same thing. We're using this as a sentinel, not because its value is less than anything else. That's a different use. Here, it's for two things. One is it makes an empty table not be a special case. So when we're talking about looking things up in the table or inserting things into the table, you'll see in a moment that we don't have to have any null question mark checks to handle an empty table differently from any other kind of table. And the other thing that's important about it is it allows us to maintain the EQ-ness of a table, even if all its elements are gone or it doesn't have any elements in the table. So imagine, if you will, that there are 4 different variables that are local to different procedures in your program that all happen to point to the same table. And let's say now that we want to cons a new pair at the front of the association list, because that's how you add an element. Well, we did that for one of the variables, and we could say set bang this variable to cons new element, the old value of the variable. But those other variables that pointed to the same table don't anymore, because the frontmost pair of the association list isn't what it used to be. Having this sentinel node avoids that problem, because any variable that points to the table points to this pair, and each table that we make will have a different one, and it's always going to stay the same. So you can rely on any set of variables that point to it continuing to point to it no matter what happens in the program. This, I guess, might sound a little abstract until we actually look at the code, so let's go ahead and do that. In this program, I defined a table this way. You'll notice that I did not say quote open parenthesis star table star close parenthesis, because we're going to mutate this table, and you're not allowed to mutate quoted lists. You can quote the elements of the list. You have to get a symbol in there. But the list itself has to be generated by your program by calling cons or something that uses cons like list or append or whatever. Okay? So back at the ranch, the current value of the table is a list of one element, star table star. Okay? If we want to extend this program for multiple tables, then instead of having a variable the table, we'll have a procedure called make table that generates a list and that has just the element, the one element star table star. Oops, wrong window. But I wanted to make these procedures really easy, so there's no argument for which table to use in these procedures. So how do we look up a key in the table? Well, the first thing we do is we assoc the key in cdr of the table. So cdr of a table is an association list. To begin with, it's an empty association list. But that's perfectly OK. We don't have to say null question mark, because assoc is perfectly happy to be given an empty list, in which case it will return what? False, not the empty list. OK. So we say, everybody always asks, why do I have this not here? Why don't I just have the clauses backwards? No special reason. I just sort of think of not finding it as a kind of base case. So I want it to come first in my code. But you could do it in the other order. That'd be fine. And just say if record. So if we didn't find it, here's where we return false. So assoc returned false. We return false also. If we did find it, we don't want to return the key value pair. We just want to return the record. So the trade-off is the user of get doesn't have to know how the table is implemented, doesn't have to know that there are key value pairs involved. But we can no longer distinguish between a value of false in the table and no value at all. That turns out to be just what we want in the adventure game project. And that's not so unusual. That a value of false means that there is no value. And you can set something to false to make it have no value effectively. So that's why this says cdr record. The thing that it's taking cdr of is a key value pair, and the cdr of that is a value. This notion of key value pairs, by the way, we're going to come back to it when we look at MapReduce, because that relies heavily also on key value pairs. OK, so a little more interesting is putting a value in the table. And we do it also starting with assoc. We want to look up the key in the table. And the reason is, if we do two puts for the same key, we don't want to waste memory by having the same key appear in the association list twice. The way assoc works, it starts at the beginning and cdrs its way down. So as soon as it finds a key that matches its argument key, it will return that key value pair. So any other key value pair that's later in the list and therefore was put in the list earlier has no effect. So we might as well not have two values for the same key. So we look to see if we found the key in the table. If we didn't find the key in the table, then what we want to do is extend the association list with a new element. So we're going to, in that case, create not one but two new pairs. This one is going to have the key and the value. And then this one is going to get spliced into the spine of the association list. OK, that's our goal. So if you look at the line below the one where the cursor is blinking, it says cons, cons. And that's because there's two pairs. If you look up at the picture of the association list on the top, you'll see that for each key value pair, there's a pair right above it, which is part of the spine of the association list. Okay? So we are going to take, first we make the key value pair. When I say first, scheme evaluates expressions from the inside out, right? So we're going to first make a key value pair, and then we're going to make a pair whose car is the key value pair we just made, and whose cdr is cdr the table, which is the head of the old head of the association list. And then finally, we set cdr the table to that new spine pair that we made. Okay, so we're splicing a new value into the table. Any questions about that? Okay, so you should by now be familiar with the idea that when we're building up a list, we build it up kind of from right to left. The head of the list is the most recently added member, because you make lists by consing onto an existing list recursively. Okay, so that's what we do if we didn't find the key in the table. If we do find the key in the table, then our job is simpler. Record is a key value pair in that case, and we just set cdr the key value pair to the new value. So that's changing the table by mutation, not to add something, but to change something that's already in it. Okay, so notice it doesn't say, the first one said set cdr the table. The table is that yellow pair up there. This time we're saying set cdr record, which is the value returned by a sock. So it's a key value pair. Questions about this? Great. Okay, so what would we do if we wanted to have more than one table? Well, we would just add an extra argument to get and put called table. And every place where it says the table, we'd just use the argument table instead. So we could have lots of tables. Each one would be a pair like that yellow pair with a star table star in the car and the association list in the cdr. By the way, why is it star table star? It's an old Lisp convention, which I don't think they follow anywhere else in this text, that sort of manifest constant symbols that are not variables, but just used in themselves, have stars around their name. It's like declaring something const in languages that have that feature. But it's not a type declaration, it's just a reminder to the programmer. So the stars are not important. We never actually look, nothing in this code ever looks at the car of that header pair, the sentinel node. That's important, or will be important in just a moment when we talk about two-dimensional tables. So even though I said at the beginning that you could use this as a kind of type tagging, in fact, we don't do any type checking. We just assume that the argument that's supposed to be a table is a table. Okay? Why is that important? Well, let me walk over to this picture. So what's a two-dimensional table? Well, first of all, look only at the stuff above where my arm is. And it looks just like any table. It has a star table star, a sentinel node at the beginning, and then it has a spine, and each element of the list is a key value pair, except this is a key 1 pair, because we're going to have a key 1 and a key 2, right? We're doing a 2D table. So what we have is a plain old table of key 1s. Now, for the value, I've put ... here, not as in goes on forever, but as in I don't want to talk about it right now. But there's one example that I actually worked out. So this pair in yellow, and this is something, it's a stupid little detail, but a lot of students get confused when they see this picture in the book, partly because the book is in black and white. So having this in yellow should really help, I think, if you're paying attention. This pair does double duty. As far as the first topmost table is concerned, this is just a key value pair, just like these ones, key value, key value. It's a key 1, the same as all those other key 1s, but now I'm showing you what its value is, namely not a table, but an association list. So the thing that confuses students is, why don't we need a star table star pair right here? The answer is this yellow pair is the sentinel node for the table that includes it along with an association list. Okay? So it's not really a key value pair. The value is the pair, right? Because this pair is the sentinel node for the second table that has key 2 value, right? So the way you look things up in a two-dimensional table is you start by looking up the first key, treating this as a one-dimensional table, and you take the answer you get from a sock, not from get, from a sock, which is this key value pair, and you say, guess what? I'm going to treat this as my value, namely the table for the key 2s that go along with this particular key 1. Okay? Questions about that? Yeah. Yeah, we're making a two-dimensional table. So it's like the table that we used for data-directed programming, where there was a row key and a column key. So the row key is key 1 and the column key is key 2. Yeah? The question is, how do you differentiate between a one-dimensional table where the values happen to be lists and a two-dimensional table? And the answer is, you built the table. You know what you're trying to do with it. If it really bothers you, you could make that first pair say star 2D table star. If you want to be able, for some reason, to pass around both one-dimensional and two-dimensional tables mixed together. But ordinarily, that's not going to be the case. Ordinarily, the application that you're using means either that all your tables are one-dimensional or that all your tables are two-dimensional. However, one of the homework problems that you're going to do is to implement multi-dimensional tables where instead of having a key 1 argument and a key 2 argument and a key 3 argument, you have one argument that's a list of keys, kind of like a type signature, where you get all the keys together in a list. And use that to look up in a structure that can have any number of dimensions. And then the way you know is that you believe the user. If the user gives you a list of length 1, then you give the user back whatever the value is for the key 1, etc. Okay? All right, so again, this is not the world's most intellectually interesting point, but it's something that trips students up a lot, how that pair serves double duty. If you look at it from above, it's a key value pair. If you look at it from below, it's the sentinel node of the second table. By the way, how long does it take to look something up in this table? Theta of what? What's n? The number of elements in the table. Nope. Somebody raise a hand. Not just mutter, because I can't hear the muttering. Yeah. The number of keys. Yes. It's the number of key 1s plus the number of key 2s in the worst case. Half of that in the average case. Because in the worst case, what we're looking for key 1 turns out to be the very last key 1. And then when we get to the second layer table, it's the very last key 2. So it's the total number of key 1s plus the total number of key 2s. So it's linear in the sum of two things. But that's less than if you implemented this table. There's a simpler way to do two-dimensional tables, which is just to make the key be a list of two words, right? And check both keys at once in a single linear table. And the problem with that is that then it would be, the running time would be the number of key 1s times the number of key 2s. Because that's how many key 1, key 2 possibilities there are. So this is a little bit more efficient in time at the cost of a little bit more complicated data structure. Okay? Right. Should we use equal or EQ when we're looking to see whether the keys match? Okay, let's take a vote. Who votes for equal? Who votes for EQ? Okay. You're both right. It depends on what you're doing. In all the situations in which we've used tables, and we'll use tables in this course, the keys are symbols. Since they're symbols, they are EQ if they're equal. So it does, oh, wait a minute, I take it back. There'll be a couple of situations coming up down the road in which we use numbers as keys. And remember I showed you last time, two numbers that are equal are not necessarily EQ if the numbers are very large, like more than plus or minus 2 billion. And so if you have numeric keys, then it's the right thing to use equal to make the comparisons. If the keys are just words, it doesn't matter. If the keys are lists, then it depends whether you mean to test that these two lists look the same or whether you mean to test that it's the identical list. So you would use either EQ or equal in that situation. Because it depends, we have actually two procedures for looking things up in association lists. The other one is called ASSQ. ASQ. Sounds kind of funny, but that's its name. Which is just like a sock, except that a sock uses equal to make its comparisons, and ASQ uses EQ to make its comparisons. Okay? So you get your choice. Okay, where am I? Oh, moving right along. This is great. Okay, memoization. So exercise 3.27 is the one that asks you to draw an environment diagram for Fibonacci numbers. And it's a big pain in the neck. If you actually did it, the diagram you got was long and complicated. But let's look at fib.scum. So what we have up here, the first procedure, fib, is the simplest, most straightforward possible way to implement Fibonacci numbers. Namely, numbers 0 and 1 are 0 and 1. So if n is less than 2, return n. And otherwise, return the sum of fib of n plus 1, n minus 1, sorry, and fib of n minus 2. Because that's the definition of Fibonacci numbers, right? Each one is the sum of the two that came before it. So if we actually do this, we can take, fib of 6, fib 15, fib of 20. See, there was a little bit of a pause there. Oops. Fib of 25 has quite a noticeable pause. Fib of 30 is already way too slow to be comfortable. So as you know, for this particular problem, there's an iterative method of doing Fibonacci numbers that runs in linear time. But I want to look, while this thing is taking its time. Ah, there we go. We finally got an answer. I want to look at this implementation. So I'm going to say fast fib of 30. What? Uh-oh. Did I make a mistake here? Fast fib 30. Huh. Oh, wrong get. Let's start again. I wanted to use the table that the two-dimensional table that we built in. And I had this one-dimensional table in the way. So let's load fib. And now I can say fast fib 30. And I get the same answer, but I get it instantly. Takes a little while, but not exponential time. It's only quadratic time. Here. Oops. Oh, I see. Control O, that's what I mean. Control N, Control O. There we go. That's how big it is. So how does this code work? It works by a technique called memoization. Which is a little bit of a tricky word. So I'll write it down. Doesn't have an R in it. It's just memoization. Although it's related to memorization, because what we do is every time we compute a value for this function, we remember it. And here's how that works. FastFib says, if n is less than 2, return n, same as before. And now, let me do a get. This is the kind of get that has 2 keys. So it's the situation I was telling you about before, where one of the keys is a number. So the first key is the word fib. That's sort of the operator that we're doing. Only instead of a data type, the other key is the number that we want fib of. So we look to see if the number is already in the table. If so, just return it. If not, then I call fastfib twice, add the results, put it into the table, and then return that value from the table. I could have used the let to put the sum in the variable result and return that, but it was just as easy to get the result. So if we look at the table, what we find is I can say get fib 100, and it's stored in the table. And I can also say get fib 99, which is a slightly smaller number, because all the intermediate results are stored in the table. Because the reason the ordinary fib takes exponential time is that it's doing redundant work. Right? Does everybody understand that? Let's draw a picture. I want fib of 100. In order to do that, I need 99 and 98. Well, for 99, I need 98, 97, 97, 96, 97, 96, 96, 95, 96, 95, 97, 96. Okay, so we're calling fib of 96. 1, 2, 3, 4, 5. Whoops, nope. Lost what I was doing. So just 4 times for fib of 96, because it's 4 down from 100, I guess. So by the time we get to fib of 3, we're calling it a bazillion times, right? Namely 2 to the 100th times, more or less. And using this table for memoization avoids that repeated calculation. So how long does this take, do you think? Theta of what? Theta of n? Theta of n squared, maybe? Okay, you might think, yeah. Good question. Well, now you know how tables are implemented. You tell me, is our table ON lookup time? No, the table that we gave you with the get and put is that table. It's one of those. So you might well think that the answer is theta of n squared, because we're making n calls to fib, and each one does a lookup that takes theta of n time. As it turns out, we're lucky about this because entries are added to the table at the beginning. So when I'm trying to compute fib of 100, it just so happens that fib 99 and fib 98 are at the front of the table. So it takes a constant amount of time each time to do the 2 lookups that we have to do. And therefore, the whole computation is theta of n. Provided that the numbers are smaller than plus or minus, well, plus, I guess, 2 billion. When the numbers get bigger than that, the computation, the adding for each number takes time proportional to essentially the number of digits in the number, which is log n. So the running time for very large numbers will be n log n. Okay? But that's, knowing more than you want to know about how numbers are implemented. Basically, as far as the table business is concerned, we're just really, really lucky about the order of things in the table. And so each lookup takes a constant time instead of theta n time. If we put things in the table in random order, then it would take theta n time to do each lookup. OK, so that's memoization. Now, we did this memoization using a particular kind of table structure that is built into our initialization file for scheme for this class. You don't have to use this particular data structure. So, when you're finished with this class, you may never again see exactly this kind of table. But you will, I promise, see memoization. And it's going to really save your life. It's going to take problems that would otherwise use exponential time and turn them into linear time, or maybe at worst quadratic time programs. So really, really, really important technique for optimization that's based on, let me remind you, the ability to mutate a data structure. Because what makes memoization work is those set cars in the put procedure. OK. Oh, which reminds me. Is fastfib a functional program? Let's take a vote. Who says yes? Who says no? Oh, come on. I think like hardly anybody voted. Here's a sideways thumb. Yeah, is that a hand up or no? OK. No, OK. It's a tricky question. It's a really complicated question. The argument for yes, which is a very good argument, is that if you pay no attention to its implementation, it is absolutely functional. Every time you call fastfib with the same arguments, you get the same return value. The argument for not being functional is that if you look down under the abstraction barrier, you can see that things are being done by mutation. So that makes it not functional. The counter-argument against that argument is every single thing you do on a computer, if you look closely enough, involves mutation. You will learn that when we get to 61C, and you learn about how computers actually work, you will find that you're doing mutation right and left, even in the most functional of functional programs. So that kind of licenses us not to look below the abstraction barrier if the program actually is functional in its behavior. Now, its behavior is a loaded term. Its input-output behavior is totally functional. Its running time behavior is not. Because if I ask for fib of some really large number like 1,000, it's going to take a while the first time. Second time, it's going to take no time at all, right? Because it's right there in the table, at the front of the table, in fact. So if in behavior you include how long it takes to do something, then you would have to say that this isn't functional. Is that ever anything other than a quibble? Yes, if you're in the computer security business. Because if you have, as is common in military applications, different people working on the same computer with different security levels, and somebody with a high security level wants to illicitly transfer information to somebody with a low security level, which really secure operating systems know about security levels, and they don't let you do that. One of the back doors to doing it is to artificially change the how busy the computer is in the high security person's program. And then the low security person's program just keeps asking the operating system, what's the load average? Meaning, how many other programs am I competing with right now? And that number goes up and down, and you can use, Morse code or something to transmit very slowly whatever information you want. Yes? Somebody said something. Oh, well, never mind. Transmit information from a high security level to a low security level. So if you're a security person, that is to say a professional paranoid, then you have to say that fastfib is not functional. For the rest of us, I'm willing to say that it is functional. Because it doesn't make any visible change in the environment. The table is all beneath the surface. And its input-output behavior is repeatable. So all of which is just a way to say that these ideas about functionality are A, very important, and B, a little complicated to really, really think through. What if we try to memoize the random procedure? Is that a good idea? No. Right? If we do memoized random of 10, the first time we call it, we get some number, 3 or 7, right? Those are the numbers that everybody picks when you say pick a number from 1 to 10. So all right, I'll pick 4 just to be different. I say random 10 and I get 4. Next time I say random 10, I'm going to get 4. The next time I'm still going to get 4, and so on forever. So if the underlying computation is not functional, then memoizing it won't work. It actually makes your program incorrect. So this is a reason that functionalness are not as important, because it helps us decide, can I optimize my program by memoizing this computation? Okay. Oh yeah, later on, when we get to streams in, I don't know, a few weeks, we're going to see another important example of an implementation of functional behavior that is not functional in the implementation. So that's an idea that's going to come back to us. Okay, any questions? We're nearing the end. Huh. For a change, I actually finished early. Okay, see you Friday. Oh, Friday we're going to talk about vectors, which are not in the textbook. So your only resource is my lecture notes, page 327, for reading about them.